Let us now study energy stored in a capacitor. A capacitor is a device which can store charges and energy also. Okay, let's study that now. So let's take a capacitor. The symbol of capacitor is two parallel lines of equal length. Then you connect it to a battery. Battery symbol is different, or cell is different. It is long line and a short line. Long line is positive, short line is negative. Then you connect it like this way. Yeah. Now, so this is a capacitor, capacitance C, and this is a cell, or we can say battery also. Now what happens is the negative end gives electrons. Okay, these electrons go from negative terminal to this plate here. This plate gets a charge here minus Q. To move the electrons from one place to next place, the cell or battery must do some work. Okay, let's study about that now. So the work done, that is W is equal to voltage into the charge here. Okay, but now you see, let's take a small work done. So that small work is dW. So dW is equal to the voltage V is constant, into the small charge. We're moving a small charge here. So dW is equal to V into dQ. Now we got this now. So let me take the formula for capacitance. Capacitance C is equal to Q by V. Cross multiply and interchange, you will get this way, that is V is equal to Q by C. Okay, so what I done is I just rearrange this. Okay, so instead of V you write Q by C. So Q by C into dQ. Left side will have dW. Okay, now this is small work. Let's see, if you want to give many charges, then we have to integrate this, and you do a lot of work. So integration of all the small works, dW is equal to integration of Q by C from limits or dQ, and the limit is 0. For starting is 0 charge. The capacitor will have 0 charge. Then finally it will have charge Q. So 0 to Q, this is the limits here. Okay, so let's integrate. Left side we will have W is equal to, and the right side we have constant, that is 1 by C. Capacitance is constant, so take it out, into integration of Q dQ, limits 0 to Q. Okay, let us see this integration. So let's take the formula. We'll recall the formula. Integration of x power n dx is equal to x power n plus 1 by n plus 1. This formula you have to use here. Okay, let's see that. So what we have is 1 by C into, open a box bracket, Q power, this is actually 1 only now. So 1 plus 1, that's 2 by 2, limits 0 to Q. Let's substitute now upper limit minus the lower limit. So you will get here 1 by C into upper limit was Q. So you will get here Q square by 2 minus the lower limit is 0. So 0 square by 2. So this will become, second term is 0. So you will have, you getting Q square by 2C. Left side we have the work done. Now this work that we do is stored as a potential energy in the capacitor. Okay, so instead of writing W, you can write as U. UE stands is, it means the symbol for potential energy. Let me write that also now. So we have UE, that means the work done is stored as a potential energy. U stands for the potential energy. In this case, electrostatic potential energy is equal to, on the right side we have Q squared by 2C. Okay, now instead of Q we must write some equation. Let's see what we get for that. We know capacitance formula, C is equal to Q by V. This is a formula for capacitance. So we must get Q, so cross multiply. So what we have, CV is equal to Q. Rearrange on interchange, Q is equal to CV. So instead of writing Q, you can write here CV. Okay, so let me write that now. So Q square we have, that means C square, V square will come. C square and V square divided by 2C. C square, this is C square, V square by 2C. So what will happen, C and the square will cancel. So you'll get the formula, electrostatic potential energy is equal to half, you can write outside, and then we saw C and the square cancelled, so half C then V square. This is the formula for the electrostatic potential energy stored in a capacitor. It's a very important formula. That means what? If capacitance increases, then energy stored also can increase. Then if voltage increases, then the energy stored also will increase. So this is an important equation. But now let us see how to get it in physical dimensions. Okay, so we design a capacitor and we must see what is the energy stored. So for that, we'll take a parallel plate capacitor. Draw a parallel plate capacitor again. This is a parallel plate capacitor. The area of the capacitor